I'm in the middle between two presentations with similar content. So I use some of the concepts already described by Elena just a few minutes ago, and I try to avoid to say too many things related to the next presentation. So the data are the same that you already saw before, and so I can skip to save time this data. I can just say that this data comes from the far side of the moon, this place, and are the only data, the only radar data on ground from the far side of the moon. And as was already told, the low frequency antennas data has a lot of problems. And while the high frequency one has a tremendous potential and are very useful and helpful to see below the ground surface for a very long path, because up to yesterday, because yesterday evening there was the last release of data made public from the Chinese agency. Until yesterday, this was the path release from here, the landing site, up to this point. And now the rover is going on that direction, still working and still ongoing. The total length is more than 1 kilometer and 300 meters, more or less. So a quite long path. This is the location of the landing site on the background. And Elena showed before analysis then to extract from such kind of data physical parameters like the electromagnetic velocity, the attenuation, the density, the electrical conductivity. Now I want to do something different, or something which is a possible combination to what was shown before. So I try to extract images of the subsurface. In terms of structures, of shapes, of layers, because radar has the ability to show reflections which are in turn correlated to any electromagnetic change in the subsurface. Actually, they're not only reflection, they are also diffraction, which was exploited for extract, for instance, some of that parameters here. The problem is that up to now, many paper was published, especially in the last 2 years, showing different interpretation of the subsurface. And in the first release, which just encompassed the first 100 meters or a little bit more, all seems to be very clear, very flat, very homogeneous. So if you see up to this point, you can see that the main horizons here, down to about 40 meters from the surface, are almost flat, almost horizontal, parallel to the surface. But then many different shapes and structures appear, and you can see that there are very different interpretations. I show you some references below. And in some specific location, there are totally different shapes, structures going up, going down, faults, fractures, strange shapes. And our interpretation, it's that we propose now, is the one in black here. This is not the total release part, but I show you something in addition to that. In any case, in any case, we can see that the first glance, nothing is horizontal, nothing is homogeneous, nothing is simple, I say. Because like on the Earth, the geology of the moon, even in the regolith, it's very, very complicated. And as much data as we have, as much complicated it is. The problem now is that how can we interpret such a complex situation in an objective, repeatable, and correct way? And we try now to exploit the deep learning techniques. So something which is automatic, obviously, then it should be checked by other techniques, as I show you later briefly. But the idea is that we try to extract automatically reflections in 1D, so trace by trace, so in vertically, so totally independent from the lateral coherence or not. So more objectively, because if some coherence appears, it should be there without any subjectivity level. And we exploit bidirectional long short-term memory. It does mean that we try to find a reflection, both starting from 0 time here up to the maximum time, but also in the reverse direction to have a double check of the results. And the results are in terms of horizon probability from 0 to 1. 0 does mean there's no horizon, most probably. 1 does mean almost surely there is an horizon. And this is repeat. Here is just for one trace. It is repeat for all the traces. These are just synthetic examples just to validate the approach. And this is what happened when we applied such an approach to the moon data. This is the horizon probability. In yellow, there is high probability. In dark blue, very low probability. But this is a detail in a quite complicated area in which there are dipping horizon combined with horizontal horizon, and there are places which were not interpreted before, like this shape or that shape, which is the correlation between this highly dipping horizon with that almost flat horizon. It was difficult to understand. Just consider the amplitude, so just consider that white or black and red values, while here they seem to be easier to be focused. For instance, this path is quite clear here, but we can do something else. If we set some thresholds, and frankly speaking, they are subjective, so you can choose a different threshold than me, or we can decide that one threshold is different from the other, but you can try and set different type of thresholds, and these are the results. There are some more, I say, objective ways to set threshold. For instance, just using the 2 sigma value or the maximum peak or the mean value or what you want. But basically, we fix 0 or 1, a binary threshold. Is there? It's not there, an horizon. And if we do that, I switch now back and ahead, and you can see in black the high probability points. So this is a more objective way to see, to extract, to fix where at least can be the horizons. If we move again to the same close-up as before, you can see that now automatically it's possible by the neural network to find the horizon here. Not only the reflection actually, but also some diffractions which are more common, especially into the regolith. Obviously, we compare such results with other analyses, which are not the topic of this talk, and we see that they are quite similar. Now, I just use a different color code to say that one horizon has a color code depending by its location and its lateral continuity, and we check that to the so-called signal attributes, which are something additional attributes, additional information, I say, embedded within the signal, and not only relate to the signal amplitude, but for instance, relate to the signal frequency, like this one, or the spectral content, thank you, or the continuity. And we see the same thing. So we are able to propose, this is just the first possible description of different units. So we can combine different horizons, automatically extracted in units. And we see the first units, which is the regolith. And inside regolith, by the way, there are craters. There are layering, which were never previously interpreted. Below, there are the second unit, which is quite complex and has subunits inside. There is a third unit, much more uniform, which is interpreted as a layered ejecta as unit 2. And on the bottom of the profile, there are the basalts. So just to conclude, the deep learning automated horizon probability approach can give us the opportunity to have a much more objective way to interpret not only the data, the radar data of the Earth, but even the one of the Moon. Why not? This is fully reproducible. Already can obtain the results, and there are a lot of new interpreted data. By the way, yesterday evening I told you that new data has been released to the public community, so the work and the road ahead is high, and we can work to interpret all the data available up to now. You can see further details, especially in the 2 papers cited, which describe deeply the algorithm that was used. Thank you so much.